So, hello student, let us continue from the previous class, and in today's class let us look at very typical problem that we face in geotechnical engineering, that is the modeling of interfaces. Because whenever there is a joint, there is a possibility for relative slip, and in geological medium it is very common for the occurrence of joints and interfaces. Because whenever we see any rock medium, you will see some joints along which the sliding could take place, or within the soil deposit there could be a thin layer of soft clay along which the sliding could take place. And when we do any finite element modeling, we should be able to capture the behavior. Apart from those natural phenomenon, we could have joints in several other cases, like for example, here we have a pile that is installed in the soil, and let us say you are pulling it out, and the predominant resistance is from the the skin friction that is acting along the surface apart from the weight of the pile. And the same thing happens even when you compress the pile. Some capacity is because of the skin friction and some capacity is because of the end bearing. And by using the special type of joint or interface elements, we will be able to simulate what is happening along the joint between these two materials, like a pile that could be made of reinforced concrete or steel, and then the soil. And in the process we should be able to get the interaction that is taking place between the soil and then the pile, and we would like to know how much of the applied loads are transferred into the soil through the pile. And in another case, we may have some geosynthetic type reinforcement in a reinforced soil embankment, and we would like to know how much pull out force that we can apply for a given length of the geosynthetic, and how the loads are transferred from the geosynthetic into the soil, and that also requires us to model the interface between geosynthetic and then the soil. Then of course, as I mentioned earlier, the rock joints is a very common occurrence whenever we deal with rock mechanics problems. And we could also have the joints between facing blocks within a reinforced soil embankment, within a reinforced soil wall, or let us say a rock joint, or sometimes we collect an undisturbed rock sample, then we see one seam that is there inside embedded as a geological formation, and we would like to know its strength and then how it is going to offer the resistance. All these things we can do by modeling with an interface element. And even in the construction industry, whenever we have a mortar wall, brick masonry wall, we may need to simulate the joints between these bricks, so that we can estimate the behavior. Then in another example is between a retaining wall and then the soil. Let us say our retaining wall is deforming away from the soil, either by rotation or by bulging out. Then what happens, should the soil stick to the retaining wall, then we will transfer unnecessary magnitudes of the shear stress into the soil. Like these are not real, but because of the numerical improper modeling, we could be transferring some additional shear stresses that might lead to failure. And to prevent that, we can place an interface between the wall panel and then the soil, so that the relative sliding can take place against the retaining wall. So, there are different types of joint elements that have been developed in the past 50-60 years. Originally in 1967, it's not exactly the joint element that we know as of now, but it was to simulate the slip between reinforced concrete and then the steel reinforcement, and they called these elements as nodal link elements way back in 1967, and later on people started using thin isoparametric elements, the continuum elements, and then later the zero thickness isoparametric elements have come in 1968, and then 1970s and 1981 there were several papers. See, these are all some of the papers that were published on the joint elements, and the first one that was published in 1967 by Go and Scordalis, that was for finite element analysis of reinforced concrete beams, and in that paper they proposed one simple element that can simulate the slip between the steel reinforcement and then the concrete. And then later on Goodman, Taylor and Brekke and others, they started working on zero thickness joint elements, initially the normal joint elements, but later isoparametric joint elements which are compatible with our isoparametric continuum elements. And the element that was developed in 1967 by Go and Scordalis is something like this. Is actually you connect 2 points, one point on the concrete and the other point on the steel through 2 springs. One is a normal spring and then the other is a tangential spring like this. So, this Kn is a normal spring between the concrete and the steel, and the Kh is the tangential spring between the concrete and the steel, and the displacements on both sides of the interface are referred to as u1 v1, u2 v2, where u's are the tangential displacements and then the v is your normal displacement with respect to your interface. And our h is the tangential spring and v is the normal spring. So, we need to define what is the tangential direction, so that we can assign the stiffness to these elements properly. And here it is, so here we have an upper surface like this and then a lower surface. One could be related to concrete and the other could be related to steel, and we have 2 springs, the black colored ones are the normal springs 1, 2, 3, and then this red color ones are the shear springs, and there is no separation between these 2 surfaces. In fact, this separation that I am showing is only just for illustration purpose, but it is not so in reality. And there are 2 nodes defined with the same coordinates, and these 2 nodes are connected with a normal spring and then a tangential spring, and we have to somehow define the tangential direction for these spring elements. That we do by defining 2 additional nodes. Basically, this element has 2 nodes between which these 2 springs, the normal and tangential springs, are connected, but then we need 2 other nodes to define the tangential direction. And we will have a shear deformation along the interface, that is u2 minus u1, where u2 and u1 are the shear displacements tangential to the interface, and the relative normal deformation is v2 minus v1, that is normal to the interface direction, and these are relative to the interface. These are not global displacements. See, the global displacements could be ux and uy, and we need to to apply the direction cosines to convert the global displacements to the element directions, and we can write the constitutive stiffness as Ks and Kn. Basically, there are two stress components, and so we will have two stiffnesses. One is in the shear direction and the other is in the normal direction, and our there are no strains, because this being an element of 0 thickness, we cannot define strain per se, because there is no length or there is no thickness. We define only the relative displacement between the two surfaces. So, if you have two surfaces, whether they are sliding against each other or they are separating out or they are compressing against each other, and that is enough for us to calculate the stresses by multiplying the relative displacement with these stiffness coefficients Ks and Kn, and the units for these are the F by L cube units, kilonewton per cubic meter. So, that this multiplied by our displacement, relative displacement, will give you the stress, either the shear stress or the normal stress. And the shear strain is ut2 minus ut1. Actually, the subscript t refers to the tangential direction. To be more specific, epsilon t is the relative shear displacement between the two nodes, node 1 and node 2, and the normal strain epsilon n un2 minus un1, that is the relative normal deformation. And in terms of the global displacements ux and uy, we can get the local displacements by applying our direction cosines, cosine theta and sin theta, like this. And then apart from these two nodes, node 1 and node 2, we define two other nodes, node 3 and node 4, for getting our tangential direction. And our epsilon t and epsilon n, the shear strain and the normal strain, can be obtained in terms of the Cartesian displacements at the two nodes 2 and 1, like this. And then we can get our global stiffness matrix as A transpose C A, where C is our Ks and Kn, the constitutive matrix. So, the C is this, and our direction cosine matrix is this, to convert from the global from the local directions to the global directions. So, actually this looks very similar to our bar element stiffness matrix, because we have the same terms like cosine square, sine square, and so on, okay, and cosine theta, sin theta for all the off diagonal terms, okay. And so, these nodal link elements that were developed in 1967, they enabled early researchers to model the slip between the two surfaces, the concrete and the steel. However, these are not continuum elements. Actually, these are discrete provided at discrete points, and these are not really compatible with the isoparametric elements, because in the case of isoparametric elements, we have seen that the corner nodes, they will have some weight factors, and then the mid side nodes, they will have some weight factors, and in the case of a 9 node quadrilateral, the center node will attract more loads and so on, we have seen. But when we use these nodal spring elements, we need to externally compute these stiffness coefficients, and that may not be possible, especially if you have a curved surface. How do we deal with the stiffness, because that depends on the curvature and so on, okay. And we cannot get a consistent load distribution between the element nodes by using the nodal spring elements along with isoparametric elements. So, these nodal link elements they have not really become popular because of these reasons. Originally in 1960s, the continuum element that was used was only 3-node triangle, in which all the nodes have equal weightage. But later we started using 6-node triangles, 8-node quadrilaterals, 9-node quadrilaterals, and so on, where the stiffness contribution at different nodes is different. That comes from the shape of the element. And later people started using the thin continuum elements. The idea is that if you place a thin continuum element and with some reduced properties for the interface, you can promote the failure along this preferential directions, that is along our weak plane. Okay. And we assign very low modulus and very low strength to these interface elements to promote early failure and enable shear deformation. But then small thickness means how small should it be, whether it should be 0.1, 0.01, 0.0001, and so on. And the main problem is we do not have any experiment to quantify the interface thickness, because that depends on the type of soil and then the type of interface, whether it is a smooth interface or a rough interface, and whether your soil is going to dilate. In that case, the effect of the interface might propagate deep into the soil, and so on. So, the optimal thickness for the interface might change with the type of problem that we have. Okay. So, it is and then when you use thin elements, the aspect ratio could be very large. So, the length to thickness ratio could be very high, but ideally for most accurate results, the length to thickness ratio cannot be more than about 2 to 3, or at the limit about maybe 5 to 6. More than that, we may start having numerical issues, especially depending on the type of element that we have. And the other problem is with the different thicknesses that you use for the interface, your properties might change. The modulus that you use, the shear strength properties that you use, you may have to calibrate a little bit so that you can get some reasonable results. So, because of these reasons, these elements have not become very popular, and another reason is the numerical issues. So, we could have singularity problems, or some unnecessary modes of deformation might develop because of these numerical issues. So, let me show you one example of using the thin interface element. So, here we have two blocks, the upper block and the lower block, and then these two are connected with a thin isoparametric element. In fact, all of them are 8-node quadrilaterals. Even this thin element is an 8-node quadrilateral, and the thickness here is 0.01 and here it is 0.1, and then actually it is the shear deformation applied for the lower part against the upper part, and we are going to monitor the shear stresses that are developed here. And if you plot a graph between the shear displacement and then the shear stress, these are the different graphs, and you see with the different thicknesses of 0.01, 0.05, 0.1, we get different result. And of course, the ultimate stress is the same, because that is controlled by the plastic limit, whereas the actual stress strain behavior is different. With the 0.01, the peak stress is reached at a very low displacement, maybe about 0.01, but with 0.1 it is reached almost at about 0.08 or 0.09, and the normal pressure that is applied on the interface is 100 kPa, and the C is 10, phi is 30 degrees, and then the tau max as per our Mohr-Coulomb relation is C plus sigma and tan phi, that is 67.74. Let me just erase this. Okay. So, here our the theoretical limit is 67.74, but the finite element predicted one is less than 60, about 57 or something. So, there is a huge difference. It is actually, as a percentage, it is about 15% difference is there between the theoretical limit and then the finite element limit that is predicted. So, that means that this model is not able to exactly replicate the strength of the interface. So, we need to go in for some other type of elements, and later, more recently, thin interface the zero thickness interface elements have become very common, and initially they were developed in the generalized coordinate method that are compatible with say the 3-node triangles or 4-node quadrilaterals, and they are only suitable for planar surfaces. But now we have the isoparametric elements that we can use these even for a curved surface. Like, let us say you have two cylinders, one rotating against the other internally, even that interface we can simulate by using these isoparametric joint elements. And once again we define these elements in terms of two strains, shear strain and then a normal strain, and we have two surfaces, upper surface and bottom surface, and this interface could be made up of either 4 nodes or 6 nodes. 4 nodes means you can only have a flat a planar surface, and with larger number of nodes like 6, or we can define with 8 nodes and so on, we can have a curve, and the nodes 1, 2, 5 are on the upper surface, and nodes 3, 4 and 6 are on the bottom surface, and let us define xi along the length and eta normal to the surface. And although I am showing with a separation, but in reality the coordinates of 1 and 4 are the same, 5 and 6 are the same, and 2 and 3 are the same. So, basically it is a line element, but then we have some normal direction. So, epsilon shear is u xi upper surface minus u xi bottom surface, and the normal displacement or the relative normal displacement is the upper surface the normal displacement minus the normal displacement of the bottom surface. And by expressing this in terms of the local coordinates xi and eta, we can work in terms of our natural coordinates that vary from -1 to +1. And here is a close up. So, this xi of +1 refers to nodes 1 and 4, and xi of -1 nodes 2 and 3, xi of 0 at nodes 5 and 6. And when we have a lower order of element like a 4-node quadrilateral or a 3-node triangle, we will only have a planar surface, planar interface. In that case, we can have a 4-node interface, 1, 2, 3, 4 nodes, and the shape functions or the mapping functions for nodes 1 and 4 are 1 plus xi by 2, because now it is actually a line element, and n2 and n3 are 1 minus xi by 2. And when you have higher order element like an 8-node quadrilateral or a 6-node triangle, we need a 6-node interface element to be compatible, and the shape functions at nodes 1 and 4 are xi times xi plus 1 by 2, and n2 and n3 are xi times xi minus 1 by 2, and at nodes 5 and 6 these are the mid side nodes, and the shape functions are 1 minus xi square. And you see these shape functions are similar to the ones that we had seen for a one dimensional isoparametric element. And the tangential displacement at the top node is n1 u1 plus n2 u2 or n1 u4 plus n2 u3. This is when we have 4 nodes, and our epsilon is bu, that is the finite element convention that we had seen earlier with continuum elements. The strain is b times u, where your b is the strain displacement matrix. In the case of continuum, the B matrix was a matrix of the shape function derivatives with respect to Cartesian coordinates, but for the joint elements, this is basically the B matrix is consisting of only the shape functions, because now our strains are only relative displacements. These are not really strains. And in the case of 6 node element, we have 3 nodes at the top and 3 nodes at the bottom, and our tangential displacement and then the normal displacement we can write in terms of the global displacements like this. And the case of axisymmetric problems will have one more strain component, that is the epsilon theta, that is the circumferential or hoop strain, and u top minus u bottom divided by radius, corresponding radial distance, can be your hoop strain. Then our stresses are shear stress and normal stress, and the tau we can obtain as Ks times the relative shear displacement, and the sigma n is Kn times the relative normal displacement, and our constitutive matrix is this, and our units are F by L cube units, and the Ks we can determine from the modified direct shear test that we perform between the two surfaces. And the Kn, actually there is no test that we can perform for determining the normal stiffness, because we do not really measure anything at the interface level, we only measure at the top surface. And the Kn is assumed to be very large when sigma n is compressive, and when sigma n is tensile, we set the Kn to a small value, not exactly 0, but some small value, so that separation can take place between the two surfaces. So, the modified direct shear box test is like this. So, all of you know how we perform the direct shear test. So, in the lower box and upper box we fill with the soil and then do some compaction, so that the density of the soil is representative of the in situ density, and then we move the lower box to cause some shear deformation at the interface, and then the corresponding stress we call as the shear stress, and then we can calculate the interface strength. Okay. And here when we do the modified direct shear test, we place the harder material in the lower box and then the softer material in the upper box. We do not do it the reverse way, because if you place soft soil or a soft material here, then hard material here, and then if you apply the pressure loading, your hard material might punch into the soft material, and then your hard material might be interfering with the shear movements, because our shear plane is predefined. As you know, in the direct shear box it is predefined, and we like our, unless your shear plane is on that surface, we will not be able to get the proper result. Suppose you place the concrete block here and it penetrates into the soil in the bottom box. When we perform the test, instead of measuring the shear strength of the interface, we will be measuring the shear strength of the concrete. So, we should be careful. So, we always place hard material in the bottom box and then the soft material in the upper box. So, from the direct shear test we will get a graph between the shear displacement and then the tau, and then the slope of this will be your Ks. The shear stiffness is d tau by d delta, okay. And the tau max of the interface we can express as a C bar plus sigma n tan delta, where C bar and delta are the interface shear strength properties, and we can determine them from our modified direct shear test by performing tests at different normal pressures like this. Here let us say that we have performed 4 different tests at different normal pressures, and then we can do some regression analysis and plot the best fitting line, and the intercept on the y axis is your interface cohesion C bar, and then the slope is your delta. So, it is actually very similar to how we perform the normal direct shear test, then how we determine the C and phi of the soil. And the stiffness matrix, the local coordinates we can get in terms of our B and D matrices as B transpose dB. Although it is written as volume integrated over the volume, but ours is a line element. So, we are going to do this integration from -1 to +1 in the isoparametric space multiplied by some factor that relates the outer plane direction, either the thickness or a unit value or the radius in the case of axisymmetric analysis. And because it is a line element, we will have only one dimensional integration, that is in the xi direction. So, we have one weight factor and then the Jacobian matrix determinant of the Jacobian matrix J. Okay. Then once we get the stiffness matrix in the local directions, we can get it in the global directions as lambda transpose k prime lambda. That is our orthogonal transformation that we have seen earlier, and our lambda is similar to our transformation matrix that we used in the case of bar elements. And for these surfaces we can get our direction cosines, cosine theta and sin theta from our dou x by dou xi and dou y by dou xi, and our determinant of the Jacobian matrix we can get as square root of dou x by dou xi whole square plus dou y by dou xi whole square. And we have already seen in the context of the pressure loading that our dou x by dou xi is mod j by 2 times cosine alpha, and dou y by dou xi is mod j by 2 times sin alpha, and this cosine alpha and sin alpha are our direction cosines. And how we operate with these interface elements is that before the failure we will assign some initial values KSI and KNI, where KSI is the one that we determine from the modified direct shear test, and the Kn is our normal stiffness. Usually we set it to a very high value, and after we reach the limit state we can relax our Ks, we can set it to some small value, and as long as our interface is in compression, our two surfaces are going to be in contact. So, we can give a very large value for this Kn, and only when we see some tensile stress, like for example you are applying a tensile loading on the interface, we would like the two surfaces to be separated out without offering any resistance. In that case the Kn can be set to a small value. Okay. So, we reformulate our constitutive matrix D in terms of KSR and KNR, and so our actually this is more we will see more of it when we discuss the constitutive modeling, but for now in the interface we strictly enforce some limit on the shear stresses that we generate in terms of the normal stress and then the shear strength properties of the interface. And so in the elastic limit, the tau and sigma n could be independent of each other, but after the failure or at the limit state, the tau max is related to sigma n through the Mohr Coulomb parameters as C plus sigma n tan phi. Okay, now let us perform the same shear test that we had done with the thin layer isoparametric element. So, here we have the interface here. The upper box is fixed against lateral deformations similar to our direct shear box test, and the bottom box is moved horizontally, and the shear zone between these two boxes is connected by a 6 node joint element, as we had seen earlier, and this is how the deformed mesh looks like, and then these are the displacement vectors. See, the upper node is moving down, whereas the bottom node is undergoing lateral deformations, combined vertical and lateral deformations. So, we see some vector like this, and this is our stress strain curve that we get. On the x axis we have the shear displacement, and the y axis we have the shear stress, and is actually the theoretical limit is C plus sigma n tan phi, that is 67.74, and what is predicted by the joint element is also the same thing, 67.74. It is exactly equal to the theoretical limit, and the peak stress is developed at a displacement of 0.007, at a relative displacement of 0.007, whereas in the previous case when we model the interface through thin layer elements, that deformation was varying a lot depending on the thickness. If you use a very thick element, the peak stress was happening at a very large deformation, and with a very small thickness it is happening faster, and so on. But then in none of the three cases that we had seen earlier, we were able to reach this theoretical limit. See, previously it stopped at about 57 or 58, whereas the theoretical limit is 67.74. Now, let us apply this joint element to some practical problem. Let us say that we are doing a triaxial compression test on a cylindrical rock sample with a joint like this, and this joint is at an angle of alpha, and we would like to know what is the maximum pressure that we can apply on the surface sigma v. The C and phi are the shear strength properties of the interface, and alpha is the angle of the joint, and that is greater than phi, and we would like to know what is the maximum pressure that we can apply without failing this interface. And see, how we can perform is, we do not know what is the maximum pressure. So, if we do not know, we cannot really apply any pressure. And see, if you look back on how we perform these laboratory tests, all these strength tests are mostly displacement control tests. In our direct shear test or in the triaxial compression test, we deform the sample and then find the response, or how much force is developed. And the same thing we can do, we can apply equal vertical displacements at the upper surface, and then see what is the reaction force developed. And as we are moving the upper surface, the stresses will be transferred to the interface element, and then it will develop some normal stress and then the shear stress. They will continue to increase with the displacement. Then at some stage the shear stress on the interface might reach a limit state, right, and then after that the upper block will simply slide relative to the lower box. In fact, this is what you see here. After some deformation, the shear strength of the joint is reached, and then the upper block will just simply slide. And so after the failure or the limit state, the normal and shear stresses on the interface will remain constant. So we can define some theoretical values by giving some numerical values. So on the shear plane, the normal stress is sigma v times cosine square alpha. In fact, these are easily derived by drawing the Morse circle, and then you know that any line drawn from the pole will intersect the Morse circle, and that gives the normal and shear stress on a plane parallel to that line. And if you apply that, you can easily derive that the normal stress on the interface is sigma v times cosine square alpha, and the shear stress is sigma v times cosine alpha sin alpha, right. And our the maximum stress on the interface tau max is C plus sigma and tan phi. The C and tan phi are the shear strength properties of the interface, and the sigma n is the normal stress on the interface, and this we can write as C plus sigma v cosine square alpha times tan phi, because our the maximum shear strength is C plus sigma and tan phi. Our sigma n is sigma v times cosine square alpha, and so we can get the maximum shear stress like this, and at the limit state the sigma t should be equal to tau max, and by equating these two we can get an equation for sigma v like this. Sigma v is C by cosine square alpha times tan alpha minus tan phi. So the C is given as 10, and then the alpha is 26.56 and phi is 20 degrees, and so this is 91.90. Actually, if the alpha is less than phi, there will not be any failure. You can apply any amount of sigma v. So that is the reason why I said that our alpha is greater than phi. That is because of this theoretical limit. So actually we are applying vertical deformations at the upper surface, and then the upper block is moving. So after the interface reaches the limit state, what would happen to the strains within the upper box? Will the strains continue to increase, or will it move like a rigid body? Okay, that we can see it by performing the finite element analysis and looking at the results. So here this is our graph between the vertical displacement and then the vertical pressure, and this is about 91.9. It is increasing, the vertical pressure goes on increasing, and at some stage it will reach the limit when your interface fails, and these dots are the locations where our stresses are computed in the continuum element, and the continuum stiffness matrix of the continuum is formulated in terms of 2-point integration, 2 points in each direction, and then for the interface element it is done with the 3 points because it is a 6-node element. And if you look at the stresses and strains in the upper block, so I am looking at this point, any point, like you can see at any point. See, our stress, vertical stress is going on increasing with strain 6.7, 13.4, 20.1, 26 and so on, and it is increasing up to about, it's increased slightly to 92, because at that point the shear limit comes into picture. Initially slight increase has happened because before, only after the stresses are calculated, we check for the yield limit and then correct. So our the maximum stress is 91.906, and you see here, until this limit, your stress, vertical stress is increasing, and then even your vertical strain is increasing. But beyond this, your vertical stress is remaining constant, and then even your strain is remaining constant. That means that beyond that point, the entire body is sliding like a rigid body. So it is from this point onwards, our upper block is moving like a rigid body, and our strains and the vertical stresses are remaining constant. So in fact, this is one of the requirements when we develop our shape functions. If there is any constant strain state that happens, we should be able to represent, and that is exactly what we are able to represent through this example. And let us look at the stresses that are developed within the interface element. This interface element is formulated in terms of 3-point integration. 1, 2, 3. These are these refer to the integration points, and this is the shear stress, and then the normal stress, and at different displacements. You see they are increasing up to this point. The normal stress of 73.661, and then the shear stress of 36.79, and beyond this point the normal and the shear stress, they remain constant. So after the limit state, they do not change. So here through this simple example, we are able to demonstrate the use of interface element for doing the modeling of the rock joints or some other weak planes. Like for example, so you have 2 layers of soil, and we can place an interface so that we can capture the stresses that are active at the interface between the two soil layers, or between a retaining wall and then soil. We can place a interface layer and see what is happening. So I think this just to conclude, see, we have seen 0 thickness isoparametric elements which are compatible, but then the main problem is we can have numerical issues. We could have especially if you have elements with very large aspect ratio, say a length of 1 and the thickness of 0.01, means the aspect ratio is 100. So we are not sure whether the results that we get with that type of element are reliable or not. So we can go in for our 0 thickness joint elements, and these are versatile, and we will see later on how we can apply them for modeling the joints between the retaining walls and then the soil, or between geosynthetic reinforcement and the soil, and so on. Okay. So that we will see after we deal with the constitutive modeling. So this is the end of today's lecture, and if you have any questions, please write to me.